In today's video, I'm going to take you on a tour of the default volumetric cloud material and describe what all these crazy nodes are doing. So let's get started. All right, so we're going to take a look at the volumetric cloud default material. And here it is. And you can see that it's kind of messy and not really that well organized. And so the first thing that I did, just to make it a little bit more clear what was going on, is I made a copy of this default cloud material and I cleaned it up. And this is going to make it a little bit easier to explain and a little bit easier for us to take a look and see what's going on. So from a very high level overview, what we're doing here is we're creating the basic shape of the cloud in this part of the graph. And then we are creating a little bit more noisy version of the cloud in this part of the graph. And then we're blending those two versions of the clouds together using the height. So high up in the clouds, we're using the noisy version, and lower down toward the bottom of the clouds, we're using just the basic soft version. If we switch back to our level, you can see that in action here. So here down at the bottom of the clouds, you can see that the clouds are kind of softer and less noisy. But then these clouds here in the upper right corner, you can see they're higher in the sky, and they also have a lot more noise in them. And there's a lot more rippling and kind of animating going on. So you can kind of see that in action here. So here's the noisy version of the cloud, the soft version of the cloud, and then we're blending those two together using our height. And then finally here at the end, we have a few parameters for controlling the extinction or the density of the clouds, and also controlling the color. So let's dive in a little bit deeper and take a look at some more details here. We'll start with a root node. And if we select the root here and come over here to the parameters, you can see that its material domain is set to volume. The blend mode is set to additive. So those are important settings for volumetric materials. Then we'll come all the way over here to the left side of the material. And you can see that we begin by bringing in the absolute world position, which is going to serve for the three-dimensional coordinates for inside the cloud volume. And then we're also bringing in time, and time is what we use to animate the cloud effects. So we take the world position combined with a scale, and we take the time, and we add the two of those together, and then we have this base noise scale. And that's a multiplier for how big we want the details in our clouds to be. We multiply the scale with time added to world position. And then we use that as our three-dimensional UV coordinates for looking up into our texture sample. So let's take a look at what this texture is doing. We'll come over here to the texture sample. We can see that we're using T volume noise shape 64. So I'm just going to double click on that. And that brings us to the topic of volume textures. So this is a pretty important principle to understand. What we're looking at here is a texture that's kind of like a flip book. And it has 8 by 8 frames, or 64 frames. But instead of each frame representing time, each of these frames is representing the slice of a three-dimensional volume. So to create a texture like this, you would use mathematics to generate three-dimensional noise, and then you would render that noise and slice it up. So you start at the bottom here with this first frame, and then move up slightly and take another slice, and move up slightly and take another slice. It's kind of like a CAT scan or a pile of individual slices, or maybe even you could call it a stack of pancakes. And so each of these represents a different height within the volume. And so we have 2 dimensions here for the width and the depth, and then the slices represent the height. Now, there are two different ways of visualizing this. We can visualize them as a grid like this, or if we come here under the View menu, I can also switch the view mode to Trace into Volume. And what that's going to do is it's going to show our view as a three-dimensional representation of the volume texture. So here we've taken all of the slices and kind of stacked them on top of each other to give us a three-dimensional volume. And this is kind of the basis for our clouds. You can see there's this pattern that's kind of puffy looking, and we're using a three-dimensional space to look up into this texture. All right, let's switch back to our material here. So here's our three-dimensional world space, and we're using that to look up into the texture. All right, the next thing that I want to do is switch back to our world here, and we're going to open up our instance and tweak a couple of the parameters. So let's open this up here. And we're going to take a look at our noise exponent and our noise scale. So if we come back over here, you can see I've got this noise scale parameter, which controls how big the details of the volume texture are going to be. And then we have our noise exponent, which is kind of like the contrast or the, well, I'll just show you. So let's turn on noise exponent and noise scale. And we can scale up our noise here, or scale it down rather. So you can see that as this value gets larger, the details in our noise get tighter and tighter and tighter. So this volume texture is tiled a lot more times now when I turn this up. So if I get really high, it's going to get really grainy. But you can see the problem here is that the texture is tiled way too many times, and you start seeing those tiling artifacts. So this particular setting, base noise scale, you get a lot more detail in the clouds if you scale it up, if you give it a higher number, but you start getting a lot of tiling artifacts. So there's an interesting balance that you have to strike here between too many tiling artifacts and soft, nice looking clouds. So this default value of 0.05 is pretty good. You might go a little bit higher than this if you wanted just a little bit more detail. Maybe 0.1 would give you some good results without too much tiling. That looks pretty good. But much higher than this, like if I go to 0.2, you start seeing the tiling. So we want to be careful. Maybe just leave that at 0.01 or maybe 0.1 or maybe 0.08. Let's do that just to give us a little bit more detail, but not so much that we get tiling artifacts. And then for the noise exponent, this is kind of like a contrast of that pattern. And the lower I make the value, the less of that detail you're going to see, and our clouds start getting really mushy. But then if I go up with it, you can see that it divides the clouds up into little cloudlet chunks. Makes that noise really strong. Since our blend mode here on our root node is set to additive, the areas that are darker in the clouds actually show up as holes in places where the clouds go away. So we want to kind of try to strike a balance here with our base noise exponent between clouds that are too mushy, where the details go away, and clouds that are too granular or too chunky looking. So somewhere in the range of between 10 and 20 is a good value. I don't know, maybe 20 is a little bit too high. So maybe let's leave it at 18. That looks pretty good. All right, so that takes care of our base cloud shape, except for one more detail, and that's volumetric advanced input. Well, what exactly is this node doing? Well, let's take a look at this. It has this output called conserve density, and we've got a value coming out. In order to understand what this node is doing, we need to scroll down here to the bottom of our graph. And you can see that I've got this other node here, which is a root node called Volumetric Advanced Output. Now this root node is specific to volume materials. And you can see that as I come down here to the bottom, there's this pin called conservative density. So I've got a bit of a graph going on here that's coming into conservative density. And then up here at the top, you can see that my output is conservative density. So what's happening is I've got this graph, which is coming in, and then this node up here in my base shape takes the same value in the graph that I created down below and outputs it here. And so the question you're probably wondering is, what does this part of the graph do? And the answer to that is, well, it defines the shape of the clouds. So I create the shape of the clouds, pass them into conservative density here, and then I get the conservative density out. And I can multiply that by the noise texture that I sampled to get the final base cloud shape. Well, let's see what happens if I just take the volumetric advanced input value, the conservative density, and pass that out without any of these noise samples. So instead of taking the result of this multiply and passing it in here, I'm just going to take this result and plug it in here and plug it in here. So we're just going to skip this entire part of the graph entirely. And I'm going to save that, and let's take a look at what we get. All right, so now you can see that our clouds have no tight detail at all because we've completely bypassed that noise. And we're basically just taking the shape of the clouds. All right, so I zoomed out a whole bunch just so you can see what's going on here. But basically, what we were looking at before, this portion of the graph here that's going into the conservative density is defining the cloud shape. So you can see I have these kind of like tall portions of the clouds, and then I also have these portions of the clouds that are a little bit more flat. So let's take a look at the conservative density part of the graph and see how these shapes are created. So here we are down at the bottom of our graph again, and you can see that I'm bringing in my absolute world position and just taking the X and the Y coordinates. So this is kind of like a top-down projection that we're doing. And then we multiply that by a scale value to control the size of the coordinates. And then we sample a texture. Well, let's take a look at this texture really quick, and you can see that the red channel looks like this. And this kind of just defines the bottom layer of the clouds. So if we come back here to our level, you can see these parts of the clouds are defined by that red channel. And then our green channel looks like this. And what this is doing is it's defining the parts of the clouds that go up really high. So these areas that are green are kind of like those cumulonimbus portions of the clouds that reach high up into the tops. You can kind of, so this cloud here in the foreground is one of the lower clouds, and then this cloud chunk here in the background is one of the higher clouds. So if we zip up here really quick, you can kind of see the differentiation of that. So we have this one layer here of the clouds that's low, and then this chunk of cloud here is defined by that green channel of the texture. So if we take a look at red and green together, the red's kind of a little bit everywhere, and the green is kind of centered in this location and this location over here. Pretty cool. And then there's another texture. So here we have the red channel, and that's just used as is. But for the green channel, we're taking that and using it as the U coordinate of UVs. And then this node here brings in the altitude of the cloud volume. So it's actually the height. And so that height is used as the V coordinate for looking up into this texture. So this texture is kind of like a cross section of the cloud, where the height of the cloud volume is the V coordinate that we use, and then the brightness of the green channel of our other texture is the U coordinate that we use. And so this is kind of a cross section of one of those really tall clouds. You can see how it's shaped kind of like a circle. And that circle shape from the top down is defined by the green channel of this texture here. And then the cross section, or the side view, is defined by this section here. So you can see how this kind of swoops up and then across the top, and then it comes down just a little bit. Well, if we're looking at our map and we fly underneath the cloud, you can see how there's this part where it swoops up, and there's the top part across the top, and then it comes down a little bit. So using these two textures together, we're able to define in the red channel of the first texture where our low clouds are, and then the green channel determines where the high clouds are going to be, and our cross-section texture determines how they're going to be shaped. So this is a pretty cool setup, how they've done this, where this texture is what the clouds look like from the top down, and then this texture is what the clouds look like from a cross-section. So we combine all that together, and then we pass it into this conservative density input on our volumetric advanced output node. Now you may be asking yourself, well, why did they take this whole piece of the graph here and put it into here when they could have just put it right up here? What's the point of going into this input and then bringing it out again? Why did you do that? Well, there's this really nice optimization that's happening with this conservative density node. Basically, what this is doing is everywhere where the result of this part of the graph is black, the engine can know that that's a place where there are no clouds. So that's defining the empty space in the volume. And when the engine knows that that space is empty, it can use that as a really nice optimization for skipping a lot of math that it has to do. When it's tracing rays through the clouds, when it's calculating shadows, when it's doing light scattering, all of those expensive calculations that we talked about in last week's video, those things can all be skipped wherever this portion of the graph's result is black. And so by passing this into conservative density, we're telling the engine, hey, everywhere where this is black, you can just ignore that space and optimize it so you're not doing math in those areas. And then we can also take that shape and use it to multiply to get the final shape of our cloud. So we're using this graph down here for two different purposes, both to shape our clouds and also to optimize away the math in the spaces where our clouds don't exist. So that's a pretty cool technique. All right, well, let's go ahead and hook things back up again the way that we had them. And the next thing that I'm going to talk about is this noisy shape portion. But in order to show you what that's doing, the first thing that I want to do is skip over that and just use this base shape portion. So instead of doing this lerp here, we're just going to go directly from this multiply and skip over what that lerp is doing there. So we're ignoring this portion of the graph and just using the base shape portion of the graph. So I'm going to save that, and let's take a look at what that looks like. All right, I don't know if you remember what it looked like before, but right now we're getting the same amount of low detail on these bottom clouds as we're getting on these top clouds. So our original material was adding in noise on the tall clouds that didn't exist on the lower layer of clouds. And so we've removed that now, and the same noise texture that we're using down here at the bottom is also being applied here at the top. So let's go ahead and hook it back up and see what the difference is. All right, cool. Can you see the difference? So our lower layer of clouds is a lot softer looking, and there's a significant amount more noise in our higher layer of clouds. Can you see that? All right, let's take a look at how that noise is being achieved. So we have our base shape of our clouds, and we're taking that value down here and combining it with this second noise sample. Again, we have our absolute world position and our time. But you can see that our scale here, our erosion scale, is a default value of 0.5, whereas up here it's a value of 0.05. So vastly different scale. We're also using a different multiply. So this one is scrolling at 0.15, and this one is scrolling at negative 0.1. So this noise is actually moving in the opposite direction of this noise. All right, well, let's take a look at this noise texture. You can see that we've got another noise volume here. And this one is really low resolution. I don't know if you can see that, but it's only a 32 by 32. If we switch our view back into depth slice mode, you can see that this is a pretty small texture. And there's not a whole lot of detail here, but it's enough that we can break up the tiling of our clouds and add more detail without needing to use a ton of texture memory. All right, so we have the same kinds of controls here. We have a power control for controlling the contrast of it. And then we have a strength control for how much erosion there is. They're calling this erosion because wherever this noise texture is black, it takes away from the contribution of this texture. And so we can tweak some of those values and see what we get. Let's switch back over here to our map and open up our instance material and take a look at our settings. So these are the settings in that second, in the detail noise area. We have the erosion exponent, erosion max, erosion new min, erosion noise scale, erosion scale, and erosion strength. Let's start out by tweaking the erosion strength just to take a look at what it's doing here. You can see that as I turn this up, it's eroding those clouds more and more. And it gets kind of weird once we go over 1. So we probably want to keep this value lower than 1. Here we get kind of like popcorn looking clouds. But as we go down, you can see that it kind of fills in the detail. And then if we get to 0, we remove the contribution of those higher clouds of that noise completely and get rid of our noise. So we don't want to do that. But the value of 0.2 is pretty good. Maybe a little bit less, or maybe just a little bit more, but we don't want to get too far away from 0.2 for this to look nice. All right, erosion scale is going to change the size of this noise. And again, this is going to be a balance between something that's too detailed and tiled versus something that is just too mushy and not enough detail. So here you can see it's just a little bit too mushy. And then here, maybe we do want to go kind of tight on this one so that we get a lot of detail. But as you can see, once again, just like with the noise texture on our lower clouds, if we tile this too tightly, we start seeing this repetitive pattern. So let's set this back to the default value of 0.5 and maybe turn it up just a little bit to get some more detail going on here, but not so much so that the tiling pattern is revealed. All right, that looks pretty cool. Then of course we have the erosion exponent here, which is the amount of contrast. And as we move this up, you're going to get the noise becoming softer. And then as we move it down, you're going to get the noise kind of eating away the cloud more and more. Now, we definitely don't want this because this is supposed to represent a cumulonimbus cloud, which is quite dense and thick. So maybe we want to keep this value kind of high. Let's go back to the default. Kind of like it at 6 there. That looks pretty cool. All right, let's switch back to our graph again and take a look at our final couple of settings. So we have our base shape clouds and noise, and then we have the extra noise that we're adding on the clouds that are higher. Down here in this part of the graph, we're actually creating our height gradient and then using that height gradient to blend between the base clouds and the noisy clouds. You can see for our height gradient, we have this node called the cloud sample attributes that let us bring in a couple of important values from our volume texture. This is the absolute altitude of the clouds. And then this is the normalized altitude of the clouds, which means that at the bottom of the cloud volume, you're going to get a value of 0, and then at the top of the cloud volume, you're going to get a value of 1. Then we have this noise height range, which allows us to adjust that a little bit. Then we saturate, and then we have a power value noise height exponent, which allows us to control the fall off curve of this height gradient. So let's take a look at these properties, noise height range and noise height exponent, and see what they do. All right, so here's our noise height exponent and our noise height range. So for range, let's start off just by setting this to 1. And you can see that the clouds at the top of the volume got a lot softer. And so what this value is going to do is the higher I make it, the more of that noise is going to be dialed in. And if I get it too high, you're going to start seeing that noise creep all the way down to the clouds that are at the bottom, which is probably something that we don't want. Can you see how now we've got the noise really dug into these clouds down here at the bottom, and it got rid of that kind of soft, cottony look that we used to have. So we probably don't want to go quite so low on that. But this is kind of nice because we can control how much of this extra noise we're passing in. So you can see a default value of 2.5, but you may want to go just a little bit higher than that, just to introduce a little bit more of the noise. Now with this noise exponent, this controls our fall off curve. So you can see as I go really high with this value, it pushes the softness further up. And then as I come down with it, it pushes the noisiness down. So you can use these parameters to kind of tune the exact results that you're looking for and get something a little bit more like that. That's pretty cool. I like what that's doing. So you can see that by tweaking these parameters here, we've been able to achieve what we were looking for. Last time I mentioned that our clouds were just a little bit lacking in detail and they felt a little bit too soft. But you can see that just using this default cloud material and tweaking those parameters, I was able to fix that problem. And now our clouds have a lot more detail further down, and they look kind of cool looking at the top as well. So I'm pretty happy with how this turned out. All right, one last look at our material here. You can see that once we use our height gradient to blend between the base cloud shapes and the clouds with the extra noise at the top, we come on over here toward our root, and we just pass the result of that lerp into a couple of nodes that control the color of the clouds and a couple of nodes that control the extinction of the clouds. And another word for that is density. So if you tweak this extinction scale value, you control how thick, how dense the cloud is, or how thin and wispy it is. And that's pretty much it. So that's how this cloud material worked. I know that when you look at this version of it, it looks pretty nutty and kind of like something that you wouldn't be able to handle or understand very well. But hopefully by reorganizing it like this and kind of breaking it down into its main components, the base cloud shape with volume noise, the extra noise with a second layer of volume noise on it, blending between those two with a height gradient, and then this part of the graph down here, which defines the cloud shapes. I hope I've been able to help you understand how this material is put together. And you can now go in here and tweak this material and make it do exactly what you are looking for. Now there is one more thing that I want to show you. We come back over here to our map. We're going to come over here to our window. We're going to come over here to our edit menu and pick plugins. There's a plugin that is really helpful if you install because it has some really great example content. So I'm just going to do a search for volume here. And it's this volumetric plugin. It says it's a library of volume creation and rendering tools using blueprints. So go ahead and install that. And once you do, it's going to ask you to restart Unreal, and go ahead and do that. So once you have that plugin installed, and if you come here to View Options and turn on Show Engine Content and Show Plugin Content, you'll have this new folder here called Volumetrics Content. Well, if we come here to Volumetrics Content, Sky, Materials, here are a whole bunch of examples of cloud materials. Now, I highly encourage you to try out a bunch of these cloud materials and see what they do. So what you'll want to do is just come here, right click on one of these and click on Create Material Instance. And then once you have that material instance, you can drag that into your volumetric clouds slot and take a look at what these do. So for example, you can see that, whoa, these are kind of cool looking. Nice. And so then you can open up this material and compare this material with the one that we just broke down. Wow, this one's quite a bit more complicated. But using that technique, taking a look at all of these different examples, you can get a really good idea for how these cloud materials are put together, what they do, how they work. And you'll even be able to create a bunch of your own cloud materials by taking ideas from those examples. So I hope you've enjoyed today's video and that you're able to take a look at the default cloud material and understand how this is working now that I've described it. And that you can take a look at these examples that are here and break them apart just like we did and see what they're doing and start building your own cloud material. Thanks a lot for watching, everybody. We'll see you next week.